Hey everyone, today I would like to discuss with you the brake system design and operation and our learning objectives. After you have watched and practiced the contents of this video, you should be able to explain the basic brake principle related to pressurized fluid in a confined space. Describe three different classifications of brake fluid. Explain master cylinder design and operation. Describe drum brake operation. Describe disc brake operation, including the advantages of disc brakes. Explain the purpose of metering, proportioning, and pressure differential valves. Describe the operation of a vacuum brake booster. Explain the operation of the parking brakes on a drum brake system. Describe the advantages of an ABS. Describe the operation of an ABS system during the anti-lock function. Explain the operation of the amber and red braking warning lights, and explain the difference between a 3-channel and a 4-channel ABS. The brake system is one of the most important systems on the vehicle. The brake system must slow and stop a vehicle in a short distance, and it must perform this function without causing steering pull or premature wheel lockup. Technicians who service brake system must be highly skilled experts because the work they perform can affect the safety and lives of those who travel in vehicles. One of the basic principles of hydraulics is that liquids are not compressible. A second principle of hydraulics used in brake systems is that pressure in a confined fluid is transmitted equally in all directions and acts with equal force on equal areas. Most brake systems make use of a brake pedal to exert a mechanical advantage on the master cylinder. If the pedal length is 10 inches and the master cylinder attaches 2 inches from the fulcrum point, then the mechanical advantage is 5:1. When 50 pounds of force is applied to the pedal, then 250 pounds of force are exerted against the master cylinder. When 250 pounds of force is applied to the master cylinder piston and the master cylinder piston has an area of 0.8 square inch, the force exerted by the fluid in the master cylinder is 250 pounds over 0.8 square inch equals to 312.5 psi. If the wheel cylinders also have an area of 1 square inch, the 312.5 psi from the master cylinder exerts a pressure of 312.5 psi in its wheel cylinder. Thus, the force of 50 pounds at the pedal may be transferred using hydraulic principles to a force of 312.5 pounds at the wheels. Brake system principles that must be understood include the following. If the master cylinder piston on bore size are decreased, the pressure exerted by the master cylinder increases for a given pressure on the brake pedal. If the master cylinder piston and bore size are increased, the pressure exerted by the master cylinder decreases for a given pressure on the brake pedal. A smaller diameter master cylinder requires more piston travel to displace the same amount of fluid as a larger piston. The force on the brake pedal and the diameter of the master cylinder piston determine the pressure in the brake system. The diameter of the wheel cylinders or calipers determines the force against the brake shoes or pads. A larger diameter wheel cylinder or caliper piston exerts more force on the brake shoes or pads. Brake fluid quality is extremely important to provide proper brake system operation. Brake fluid must have these qualities. Brake fluids must provide a controlled amount of swell in cups and seals to provide adequate sealing in calipers, wheel cylinders, and master cylinders. Excessive swelling of cups and seals causes brake drag and inadequate brake response. Brake fluid must operate at temperatures from 104 degrees Fahrenheit or negative 75 degrees centigrade to 500 degrees Fahrenheit or 260 degrees centigrade. Brake fluid must be compatible with rubber in master cylinder cups, wheel cylinder cups, caliper seals, and brake hoses. Lubricating ability. Braking fluid must have a satisfactory lubricating ability to provide smooth operation of brake components. Resistance to evaporation. Brake fluid must resist evaporation at high temperatures. Anti-rust and anti-corrosion. Brake fluid must combat rust and corrosion in brake system components. The DOT designates that brake fluid must meet classification standards established by the SAE or the Society of Automotive Engineers. The following brake fluid classification are used at the present time. A brake fluid classified as DOT3 has a minimum dry equilibrium boiling point or ERBP of 401 degrees Fahrenheit or 205 degrees centigrade, and a minimum wet equilibrium boiling point or ERBP of 284 degrees Fahrenheit or 140 degrees centigrade. A brake fluid classified as DOT4 has a minimum dry ERBP of 446 degrees Fahrenheit or 230 degrees centigrade, and a minimum wet ERBP of 311 degrees Fahrenheit or 155 degrees centigrade. A brake fluid classified as DOT 5.1 has a minimum dry ERBP of 500 degrees Fahrenheit or 270 degrees centigrade, and a minimum wet ERBP of 365 degrees Fahrenheit or 185 degrees centigrade. A brake fluid classified as DOT5 is silicone-based, and this fluid has a minimum dry ERBP of 500 degrees Fahrenheit or 260 degrees centigrade, and a minimum wet ERBP of 350 degrees Fahrenheit or 180 degrees centigrade. DOT5 has a purple color added for identification purposes. Always use the brake fluid specified by the vehicle's manufacturer. Brake fluids in use today are DOT3, DOT4, DOT5, and DOT 5.1. The purpose of the master cylinder is to supply brake fluid pressure to the wheel cylinders or calipers during a brake application. If fluid pressure is not available in one section of the master cylinder, fluid pressure in the other section is applied at two wheels to stop the vehicle. The master cylinder may be manufactured from cast iron or aluminum. Cast iron master cylinders have an integral reservoir, and removable plastic reservoir is used on aluminum master cylinders. A cover bail is used to retain the cover and gasket on top of the master cylinder. The primary and secondary piston are mounted in the master cylinder. Rubber caps are used to seal this piston in the master cylinder bore. A spring behind its piston holds the pistons in the released position. Steel brake lines and brake hoses are connected from the master cylinder to the wheel cylinders or calipers. On rear-wheel drive vehicles, the primary piston outlet is connected to the front brake and the secondary piston outlet is connected to the rear brakes. This is a front rear split brake system. On many front-wheel drive vehicles, the brake system is diagonally split, so the primary master cylinder piston supplies fluid to the right front and rear brakes, and the secondary piston supplies fluid to the left front and rear brakes. This is diagonally split brake system. When the brake pedal is depressed, the primary piston moves down the master cylinder bore and the primary cap seals the vent port. This action seals the primary piston cylinder and forces fluid from the primary outlet ports. Pressure in the primary bore moves the secondary piston down its bore, and the vent port is sealed by the secondary piston cup. Further movement of the secondary piston forces fluid from the secondary outlet to the wheel calipers or cylinders. When fluid is forced from both outlets, the brakes are applied on all four wheels. If the brakes are applied repeatedly, the brake fluid may become very hot. Under this condition, the fluid expands and some fluid flows back through the vent ports when the brakes are released. The vent ports prevent excessive pressure buildup in the brake system. If the brake shoe adjustment is not correct or air enters the brake system, excessive brake pedal movement is required to apply the brakes. Under this condition, the driver may pump the brake pedal rapidly to apply the brakes. This pumping action may cause a pressure drop in the master cylinder because the fluid cannot flow back from the wheel cylinders or calipers as quickly as the master cylinder pistons can move when the brakes are released. When the pressure drops in the master cylinder, atmospheric pressure on top of the fluid in the reservoir forces fluid past the cap seals into the piston bores. On a cast iron master cylinder, the rubber cover gasket seals the cover to reservoir, preventing moisture from entering the system. A wire cover retainer holds the cover on the master cylinder. Atmospheric vents are located between the cover and the gasket. If the fluid level goes down the reservoir, the bellows on the cover gasket expand into the reservoir and air flows through the vents into the area between the cover and the gasket. Some drum brake master cylinders have residual valve at the outlet connected to the drum brakes. This residual valve is only used for drum brakes and maintains a slight pressure in the brake system that keeps the wheel cylinder cups expanded outward to provide improved cap sealing. Other brake systems have wheel cylinder cup expanders in place of the residual valve. In a drum brake system, the brake shoes are forced outward against the drum by the wheel cylinder pistons. Each wheel cylinder contains two pistons and cap seals with expanders. The expanders prevent air from entering the system when the pistons and caps are moving. A spring is positioned between the piston caps. A rubber dust boot is mounted on each end of the wheel cylinder. The push rods are located between the pistons and the brake shoes. The push rods fit snugly in the dust boot openings. The dust boots keep contaminants out the wheel cylinder. The wheel cylinder is bolted to the backing plate and a bleeder screw is mounted in the back of the wheel cylinder. The bleeder screw allows air to be bled from the wheel cylinder and brake system. Drum brake shoes are made from stamped steel. The brake linings are riveted or bonded to the brake shoes. The curvature of the brake shoes and linings matches the contour of the brake drums. Brake linings must be able to withstand extreme heat. The brake linings may be organic, semi-metallic, metallic, or synthetic. Organic brake linings are made from non-metallic fibers bonded together to form a composite material. Organic brake linings contain friction modifiers that may include graphite and powdered metals. Fillers, binders, and curing agents are used on organic brake linings. Drum brakes are either servo type or leading trailing. In a servo type, the brake shoe return springs hold the shoes against the anchor pin mounted in the top of the backing plate. An adjustment mechanism is located between the lower ends of the brake shoes, but the lower ends of the brake shoes are not connected to the backing plate. The edges of the brake shoes contact the support pads on the backing plate. The primary brake shoe is positioned toward the front of the vehicle, and the secondary shoe is positioned toward the rear of the vehicle. When the brakes are applied, pressure from the master cylinder forces the wheel cylinder pistons outward. As these pistons move outward, the push rods force the brake shoes outward against the brake drums. Friction between the brake shoes and the drum provides a braking action. The brake system changes the kinetic energy of the moving vehicle into heat energy through the application of friction. Kinetic energy is energy in motion. This friction between the brake linings and the brake drums creates a great deal of heat, and the drums expand as they are heated. When the drums expand, the brake shoes must move further outward to provide braking action. This additional shoe movement causes increased brake pedal movement and brake fade. Brake fade occurs on drum brakes when the drums become very hot during hard, repeated braking. Under these operating conditions, the drums expand and the shoes must travel further outward to provide braking action. Increased shoe movement requires greater pedal movement. When the primary shoe is forced against the drum surface, the wheel rotation tends to transfer movement to the secondary shoe by a servo action and force the shoe against the brake drum surface. Servo action occurs when the operation of the primary shoe applies mechanical force to the secondary shoe to assist in its application. Therefore, the secondary shoe is forced against the brake drum by movement from the primary shoe and brake drum, and also by fluid pressure in the wheel cylinder. In a servo type brake, approximately 75% of the braking force is from the secondary shoe. Therefore, the secondary shoe has a longer lining compared to the primary shoe. The adjusting mechanism between the lower end of the brake shoes contain a threaded star wheel with two extensions that fit over the lower ends of the brake shoes. In a leading trailing brake system, there is less servo action. When the leading shoe is forced against the drum surface, the wheel rotation tends to force the shoe against the brake. Drum surface. Some servo action occurs when the leading shoe presses against the anchor pin at the bottom of the backing plate and applies some mechanical force itself to assist in its application. However, the trailing shoe is forced against the brake drum by movement from fluid pressure in the wheel cylinder alone. In a leading trailing type brake, more of the braking force is from the leading shoe during the forward stop, and more of the braking force is from the trailing shoe during a reverse stop. Both shoes have the same length linings. The adjusting mechanism is between the upper ends of the brake shoes and contains a threaded star wheel with two extensions that fit over the upper ends of the brake shoes. Most drum brakes have a self-adjusting mechanism. The self-adjusting mechanism for the servo-type brake contains a cable attached to the anchor pin. The adjusters are usually opposite the anchor pin. The lower end of this cable is connected to a pivoted adjusting lever mounted above the star wheel. A spring holds the adjusting lever downward against the star wheel. As the brake lining wears, the outward shoe movement increases when the brakes are applied. During a brake application in reverse, the secondary shoe moves away from the anchor pin. If the lining is worn enough to allow sufficient shoe movement, the spring pulls the adjusting lever down enough to rotate the star wheel to the next notch. This action lengthens the star wheel assembly and moves the brake shoes outward so the linings are closer to the drum surface. The adjuster for the leading trailing brake is similar to that of the servo type brake, except it is found near the wheel cylinder. A disc brake has a cast iron disc or rotor mounted on the wheel hub. Both sides of the rotor have machined surfaces. During a brake application, the brake pad linings contact both sides of the rotor. Many front brake rotors have ventilating slots between the two sides of the rotor to act as a fan and dissipate the heat from the rotor. The caliper and brake pad assembly is mounted over the top of the rotor, and the caliper is bolted to the steering knuckle. Many calipers contain a single piston mounted in the caliper bore or in board side of the caliper. This type of disc brake has a floating caliper. A floating caliper is mounted so it is free to slide sideways on the mounting bolts. The brake hose is threaded into the back of the caliper, and the bleeder screw is also positioned in the rear of the caliper. The brake linings are bonded or riveted to the brake pads. Similar materials are used in the brake linings on drum and disc brakes. Metal locating tabs on most brake pads retain the pads to the caliper. The piston caliper has a seal around the outer diameter of the piston. A dust boot is mounted between the caliper piston and the housing to keep contaminants out of the caliper bore. When the brakes are applied, the caliper piston is forced outward. This movement pushes the inboard brake pad lining against the rotor. This action forces the floating caliper inward, so the outer brake pad lining is forced against the outside of the rotor. When the brakes are applied, the piston caliper seals twists. After the brakes are released, the seal returns to its original shape. This seal action pulls the caliper piston and brake pad linings away from the rotor surface. As the brake pad linings wear, caliper pistons move outward. This eliminates the need for adjusting disc brakes. These brakes do not experience brake fade because as the rotors are heated, they expand and move slightly closer to the brake pad linings. These brakes do not provide any servo action. Many disc brakes have a wear indicator attached to one of the brake pads. When the brake pad lining wears a specific amount, the wear indicator contacts the rotor, causing a scraping noise that alerts the driver about the brake problem. Brake lines are made from seamless steel tubing that is coated with zinc or tin for corrosion protection. Brake lines must conform to Society of Automotive Engineers or SAE standard J1047, which requires that an 18-inch section of tubing must withstand an internal pressure of 8,000 psi, pounds per square inch. Brake lines may have an inverted double flare or an International Standard Organization flare or ISO. The inverted double flare has the end of the tubing flare out and then it is formed back onto itself. An ISO flare has a bubble shaped end formed on the tubing. Different fittings are required with each type of flare, and these fittings are not interchangeable. Brake tubing is specially bent to fit a specific location on the vehicle. When a brake lining is leaking, the complete line must be replaced, not repaired. It is preferable to replace brake lines with the OEM pre-shaped brake line. Brake hoses are a flexible connection between the chassis and the wheel calipers or cylinders, or between the rear axle and the chassis. Brake hoses must conform to the SAE J1401 standard that requires the hose to withstand 4,000 psi pressure for 2 minutes without bursting. Brake hoses contain an inner liner surrounded by the metal fabric plies, a rubber separator layer, an outer jacket. These fittings are attached to the hose during the manufacturing process. The metering valve is connected in the brake line to the front brakes. The metering valve is used on vehicles with front disc brakes and rear drum brakes. During a brake application, the metering valve delays the fluid pressure to the front brakes momentarily until the rear brake shoes are forced outward against the drums. During a brake application, vehicle inertia and momentum tend to shift the vehicle weight forward. This weight shift is proportional to braking force and the rate of deceleration. This weight shift reduces traction between the rear tires and the road surface, which may result in rear wheel lockup. To provide maximum braking, equal friction must be maintained between the front and rear tires and the road surface. During a brake application, the proportioning valve modulates pressure to the rear brakes to prevent rear wheel lockup. The proportioning valves may be integral in the master cylinder or they may be external to the master cylinder. A pressure differential valve is connected in the brake lines from the master cylinder to the front and rear brakes. A wire from the brake warning light in the instrument panel is connected to a switch in the pressure differential valve. If the brake fluid pressure is equal in both the primary and secondary sections of the master cylinder, the switch in the pressure differential valve remains open. If one section of the master cylinder is low on brake fluid and the pressure in this section decreases, the piston in the pressure differential valve moves toward the section in the pressure differential valve with the low pressure. This piston movement pushes the stem upward in the brake warning switch and closes the switch contacts. Under this condition, current flows through the brake warning light. The switch contacts to the ground and the brake warning light is illuminated to warn the driver that a brake problem exists. Some brake systems have the pressure differential valve combined with the metering and proportioning valves in a combination valve assembly. Pressure differential, metering, and proportioning valves are non-serviceable components. Most vehicles are equipped with a vacuum brake booster. The brake booster is connected between the master cylinder and the brake pedal. A push rod is connected from the booster to the brake pedal, and another push rod is mounted between the brake booster and the master cylinder. The brake booster operates in three modes: release, applying, and hold. When the engine is running, manifold vacuum is supplied through a hose to the booster. If the brakes are released, manifold vacuum is supplied to both sides of the booster diaphragm. This diaphragm does not exert any force on the master cylinder pistons. This is the release mode. When the brakes are applied, the brake pedal movement closes the vacuum passage to the rear of the booster diaphragm and opens an atmospheric pressure port to allow air pressure on the rear side of the diaphragm. Because manifold vacuum is supplied to the front side of the diaphragm, an atmospheric pressure is provided on the rear side of the diaphragm. The diaphragm is moved toward the master cylinder with considerable force. This is the apply mode. Under this condition, the diaphragm moves the push rod and supplies force to the master cylinder pistons to provide brake assist. When the brakes are being held at the desired stopping force, both valves are closed to trap vacuum and atmospheric pressure and keeps the diaphragm in a hold position. A reaction disc between the booster diaphragm and the master cylinder pushrod provides brake pedal feel to the driver. This is the hold mode. Some vehicles have hydro boost brake system with a hydraulic brake booster. These systems are often used on a diesel engines because of the low manifold vacuum in these engines. In a hydro boost brake system, a hydraulic brake booster is mounted between the master cylinder and the brake pedal. The power steering pump supplies fluid pressure to the hydro boost unit and the power steering gear. Some vehicles have a separate pump for the hydro boost system. When the brakes are released, power steering pump pressure forces fluid through the hydro boost unit, but this pressure is not applied to the master cylinder pistons. If the brakes are applied, brake pedal movement operates a lever in the hydro boost unit and opens a valve that supplies power steering pump fluid pressure to the master cylinder pistons and provides brake assist. Parking brakes are applied by a foot or hand operated lever in the passenger compartment. When the parking brakes are applied, a switch on the parking brake applied draws the red brake warning light in the instrument panel. A release handle on the parking brake lever is pulled to release the parking brakes. Some parking brakes have a vacuum operated release mechanism that releases the parking brake when vacuum is applied to the vacuum diaphragm in the parking brake release actuator. This type of parking brake also has a mechanical release lever to release the parking brake if the vacuum actuator is not operating. A cable is connected from the parking brake lever to an equalizer under the vehicle. Dual cables are connected from the equalizer to the rear brakes. When the parking brakes are applied, the cable in its rear wheels pulls a lever that forces the secondary and primary brake shoes outward against the drum to apply the brakes. Some rear disc brake systems have a small drum brake inside the rotor that is used for the parking brake. This drum in a disc rotor is sometimes called a drum in hat. If the vehicle has a rear disc brakes, the parking brake cables are connected to a lever on the rear brake calipers. When the parking brakes are applied, the cable and lever turns a threaded actuator screw inside a nut with matching threads. As the actuator screw is rotated by the parking brake cable and lever, the nut moves inward and pushes the caliper piston so it forces the brake pad lining against the rotor to apply the brakes. Today, many vehicles use anti-lock brakes. Anti-lock brake systems or ABS are designed to prevent wheel lockup under high or heavy braking conditions on any type of road conditions. The main purpose of the ABS is to help the driver retain directional stability or control of steering, stop the vehicle as quickly as possible given the road conditions, and retain maximum control of the vehicle. The anti-lock braking system can be thought of as an add-on system to the normal braking system of the vehicle. The vehicles equipped with ABS still require conventional brake service work to be performed for normal brake concerns. Brake lines, hoses, calipers, drums, and friction components still require the regular attention of the technician. ABS systems are usually one of the three types. One-channel ABS in which both rear wheels are controlled together. Three-channel ABS in which each front wheel is controlled individually and the rear wheels are controlled together. And four-channel ABS in which both front wheels are controlled individually and both rear wheels are controlled individually. The ABS system should operate only when wheel lockup is imminent. The anti-lock braking system can be thought of as an electronic hydraulic pumping of the brakes or stopping of the vehicle under panic conditions or under adverse road conditions. It is a myth for one to think or believe that the anti-lock braking system will prevent the wheel from skidding. Although it does prevent complete wheel lockup, it does allow some wheel slip in order to achieve the best braking. During ABS operation, the slip will be between 10% to 20%. Slip rate of 15% means that the velocity of a wheel spent less than that of a free rolling wheel at the same vehicle speed. In the event of an ABS system failure, the brake system should operate as a conventional braking system without the benefits of ABS. The components that comprise the ABS include the electronic control unit or ECU, hydraulic control unit or HCU, wheel speed sensor, as well as the brake booster and master cylinder. The purpose of the ECU is to receive signals from the wheel speed sensors and to operate the hydraulic control unit to control the brake pressure of the wheel according to the data analyzed. The hydraulic control unit function is to modulate the pressure to each of the wheels. It receives the signals necessary to do this from the electronic control unit or ECU to apply or release the brakes under ABS conditions. If a wheel lock up during a brake application, the tire exhibits a loss of traction. Conversely, if enough braking force is applied to the tire slips to a certain extent without wheel lockup, traction increase is experienced. This traction increase is higher at 10% to 20% tire slip on the road surface. If there is 20% tire slip, the wheel is turning at 80% of the vehicle speed. An ABS is designed to provide approximately 10% to 20% tire slip without experiencing wheel lockup during the anti-lock brake function. This action provides tire traction while braking, and stopping distance may be reduced depending on the road surface and other variables. Cornering tire traction also decreases significantly if the wheel lockups during the brake application. Wheel lockup and reduced cornering traction during a brake application may result in loss of steering stability and control. If the tire slips about 15% without wheel lockup or cornering traction is greatly improved. Since the ABS provides about a 15% tire slip without wheel lockup, even during panic stops, steering control and vehicle stability are significantly improved. If a wheel or wheels lock up during a panic stop, the vehicle may swerve sideways and the driver may lose steering control. An amber ABS warning light is mounted in the instrument panel or in the roof console. When the ignition switch is turned on, the control module performs a check of the ABS electrical system. This check requires 3 to 4 seconds, and during this time, the ABS warning light is on. If the ABS warning light is on, with the engine running, the module has detected a defect in the ABS. Many ABS systems also have a red brake warning light. If this light is illuminated with the engine running, the parking brake is applied or 1 second of the master cylinder is low on brake fluid caused by a pressure differential between the two sections of the master cylinder. In some ABS, the control module illuminates both the amber and the red brake warning lights when certain serious defects occur. Under these conditions, the ABS is disabled and the system will operate as a conventional power brake system. Many vehicles have a four-wheel ABS system with a wheel speed sensor at each wheel. A tooth ring on the wheel hub rotates past the tip of the wheel speed sensor. This can be mounted on the half shaft outer joint. On some front-wheel drive cars, the wheel speed sensor are integral with the wheel hubs and cannot be serviced separately. As the wheel rotates, a tooth sensor ring passes by a sensor which is made with a coil and magnet. As the high and low spots of the teeth pass, the sensor on AC voltage is induced in the coil. The different signals from each wheel are analyzed by the ECU. An appropriate action will be taken by the ECU to modulate brake pressure if necessary. Some vehicles have an ABS with the solenoid valves, low pressure accumulators, pressure pumps, and a control module designed into one unit. This type of ABS has a conventional vacuum brake booster to provide brake assist. The solenoids in this system are referred to as isolation and dump valves. The VSS in the transmission extension housing also acts as a rear wheel speed sensor and sends voltage signals to the ABS control module and the PCM. One pair of solenoid controls the brake fluid pressure to both rear wheels in this three-channel system. Many vehicles are equipped with four-channel ABS. All the solenoid valves are mounted in a valve block attached to the master cylinder. A three-channel ABS, a pair of solenoids at each front wheel, but only one pair of solenoids for both rear wheels. These systems cannot modulate the brake fluid pressure to each rear wheel individually. A four-channel ABS has a pair of solenoids at each wheel, which can modulate the brake fluid pressure. During a brake application, if a wheel speed sensor signal indicates to the control module that a wheel is quickly approaching a lock-up condition, the module closes the normally open solenoid connected to the wheel caliper. This action prevents any further increase in fluid pressure to the wheel caliper. In a few milliseconds of the wheel speed sensor still indicating that wheel lockup is about to occur, the module opens the normally closed solenoid and allows some brake fluid out of the brake caliper back into the master cylinder reservoir. This action reduces pressure in the caliper and prevents wheel lockup. The module pulses the solenoids on and off to maintain maximum braking force without allowing wheel lockup. When the module pulses the solenoids on and off during the anti-lock function, the driver may feel pedal pulsations. Shows the hydraulic schematics on a Bosch three-channel ABS system. When a wheel speed sensor signal indicates wheel lockup is about to occur, the control module energizes the isolation valve. This valve closes the fluid passage between the master cylinder and the wheel that is about to lock up. If wheel lockup is still imminent, the control module energizes the dump valve that allows some brake fluid out of the wheel cylinder or caliper back into the low pressure accumulator. The control module pulses the dump valve on and off very quickly to apply maximum braking force without allowing a wheel lockup. During a prolonged brake application, the repeated cycling of the isolation and dump valves takes fluid out of the master cylinder and places it in the low pressure accumulators. For this reason, the control module starts the ABS pump motor when the system enters the anti-lock mode. This pump forces brake fluid back against the master cylinder pistons onto the isolation valves. This action maintains brake pedal height during the anti-lock mode. The anti-lock mode, the driver may feel pedal pulsations and a limited brake pedal fade followed by upward brake pedal movement. Many vehicles have a four-wheel ABS system with a wheel speed sensor at each wheel. A tooth ring on the wheel hub rotates past the tip of the wheel speed sensor. On some front-wheel drive cars, the wheel speed sensors are integral with the wheel hub and cannot be serviced separately. Some four-wheel ABS have a high-pressure accumulator mounted on a master cylinder. The high-pressure accumulator contains on a heavy diaphragm in the center of the accumulator. A nitrogen gas charge is permanently sealed in the upper accumulator chamber above the diaphragm. A pump integral with the master cylinder pumps brake fluid into the lower accumulator chamber. The pumps maintain a brake fluid pressure of 2,000 to 2,600 psi or 14,000 to 16,000 kilopascals in the accumulator. If the accumulator pressure drops below 2,000 psi or 14,000 kilopascals, a pressure switch on the master cylinder signals the control module to start the pump motor and increase the pressure. That's it for today's topic, and thank you very much for watching this video. Don't forget to subscribe, like, and share. Thank you for watching.